Here's a simple looking video about electric field strength. Have a go at it and then come back to this video when you're ready. I'm also going to give a few hints as we go along, so remember to hit pause when you think you can go alone. The first important point is to remember that electric field strength is a vector. So, direction is important. The second hint is that point P is between the two charges, so you're going to have to be very careful with those directions. Right, so the way to approach this, like any vector problem really, is to deal with one bit at a time, then add them together. That means I'm going to work out the electric field strength at P due to Q1, then the electric field strength at P due to Q2, then add them together. The equation we'll use is E equals KQ over R squared. So E1 equals K times 2 times 10 to the minus 6 over 5 times 10 to the minus 3 squared. Which is K times 2 times 10 to the minus 6 over 25 times 10 to the minus 6, giving me 2k over 25. I'm just going to leave it in terms of k, I think. Now this was a positive charge, meaning the electric field is going from left to right. So we just calculated that at P, the electric field due to Q1 is positive 2k over 25 to the right. That might seem like a lot of detail there, but it's important. Moving to Q2, the same equation gives us E equals K times minus 4 times 10 to the minus 6 over 25 times 10 to the minus 6, giving me minus 4k over 25. Now here's the tricky bit. Point P is to the left of Q2. So what we actually calculated is that the field strength due to Q1 at point P is negative 4k over 25 to the left. Negative 4k over 25 to the left is the same as positive 4k over 25 to the right. These are vectors, remember. So, combining these two vectors means we are adding together positive 2k over 25 and positive 4k over 25, giving us 6k over 25. With k being 8.99 times 10 to the 9 meters per farad, it comes to around 2.2 times 10 to the 9 volts per meter. Now, if you got that wrong, don't stress because almost everyone does. But do go back and understand what was going on though, especially if the positive and negative bit threw you. Let me just go over that again quickly anyway. Let's just consider Q2. Point P is on the left, and we calculated that at that point EP equals minus 4k over 25. Now if you consider another point the same distance away but on the right side, I'll label that one R. Clearly the electric field strength due to Q2 is ER equals minus 4k over 25. In fact, all around at that distance the electric field strength is equal. But it's also clear that the electric field is pointing in different directions. That means we can say that at R, the field strength is minus 4k over 25 to the right. At P, it is minus 4k over 25 to the left. With vectors, if the direction reverses, we can just change the sign. So minus 4k over 25 to the left becomes plus 4k over 25 to the right. Now, with both our electric fields pointing in the same directions, mathematically speaking, we were then able to add them and complete the problem. And just to round off, imagine putting a positive charge at P. It would be pushed to the right by Q1 because Q1 is positive, and it would be pulled to the right by Q2 because Q2 is negative. So it makes perfect sense that the electric field strength at point P is larger than what's due to Q1 or Q2 alone. We must add them together to get a larger magnitude for the electric field strength, and hence a larger force on the charged particle.